Did this in chapter 5, section 6 or 7, where you take something that is not, actually that one looks even more difficult. Not that it's impossible, so we'll still do it. I was looking at the denominator. It's not so easily factored or put into a completing the square, but this is where if you look at the derivative of the denominator, it's not exactly equal to the numerator. It's pretty close. In this case, it's you get the 4x part by taking the derivative of 2x squared, but there's no 3. So this is kind of an easier version of what we did. We already know how to do. So what you could do is you could, I don't know if I got it written down here. Okay. We'll come back. I'll let you get that if you didn't quite get it. But what we can do is we can add 3 to the numerator. So we end up with 4x plus 3 over 2x squared plus 3x plus 9 times dx. And then we'd have to subtract 3. So you just add and subtract the same thing. And one of these, this part can be handled by the natural log. If you make the substitution u is equal to 2x squared plus 3x plus 9, then du is equal to 4x plus 3 dx. So that part's easy. That's going to end up being the natural log of the absolute value of 2x squared plus 3x plus 9. This one, you'd have to rewrite the denominator into a complete square plus a constant. So that was the part that I thought, oh, that's not quite so easy, but we'll do it anyway, just to show you that. So what I'm going to do is I'm just going to do the completing the square separately. So the way you do that is you take that denominator and we just move the 9 over there, and then you'd factor the 2 out. So you'd have 2 times x squared plus 3 halves x. And then you would take the coefficient in front of the x term and square that, which would be 9/4. So let's make some space for that. So you would add 9/4 to the quadratic expression here. And what we're doing there is actually we're adding 9/4, but we're multiplying by 2, so that would really be 9 halves. So if you take 2 divided by 4, you get a half. So we're really adding 9 halves, so you'd have to subtract 9 halves. And therefore, this finally would be 2 times x plus, wait a second, yeah. No, I did something, well, no. I've done something wrong, haven't I? I missed one step, sorry. Messed you up there. So you take 3 halves and you divide by 2 and you square it. I forgot this dividing by 2 bit. So that's the same as 3/4 divided by, so that's 3/4 squared, which is 9/16. So I should be adding 9/16. So now I'm actually adding 9/8. So I have to subtract 9/8. Okay, so now we can do it because you take this term, the thing divided by 2. So he'll have x plus 3/4 quantity squared, and here we have 9/8 minus 9 minus 9/8. That's 72/8. 72 minus 9 is 63/8. So you'd have plus 63/8. So ultimately what we'd have over here is 3 times the integral of 1 over 2 times x plus 3/4 quantity squared plus 63 over 8 dx, whole thing's times dx. And that fits into the form for the arctangent back in chapter 5. So in this case, u would be equal to, or u squared is going to be equal to, u squared is equal to 2 times x plus 3/4 squared. So u is equal to the square root of 2 times x plus 3/4 squared, and a squared equals 63 over 8, so that a is equal to the square root of 63 over 8. And so finally, the final answer here on the second part is going to be 3 times, so it's 1 over a, so that a is the square root of 63 over 8 times the arc tangent of the square root of 2 times x plus, and I shouldn't have that square right there. I'll get rid of that. X plus 3/4, all divided by a, which is 63 over square root of 63 over 8. So the hard part is not breaking it up into two integrals. The hard part is fitting the second integral into a form that you can use the integral associated with the arctangent. The integral of 1 over u squared plus a squared is equal to 1 over a times the arctangent of u over a. So that's where that came from. You would look that up in the table. You wouldn't need to know that. So anyway, that's the last. So let me just here's the homework if you didn't give me enough time the first time. So we're going to move on to section 2. Thursday we'll go back and do some more from chapter 7. I just didn't have time yesterday to come up with anything coherent to talk about, so I figured we'd move on and then go back. Okay, that's probably enough time. Okay, so we're going to go on to talk about integrating factor. So here you can see that we skip over section 6, so we're going to sections 1 through 8 in chapter 8. And don't write this stuff down yet, just write the title of the section down. So it's called integration by parts, and it's kind of like integrating factor in some ways. It ends up being where you use the product rule. It's where you use the product rule, but kind of in a different format. So a lot of times it involves products, the integral of product of two terms. What this scratch in here was about was, we do know how to take the derivative of the natural log. That's 1 over x. We know how to take the integral of 1 over x, which is the natural log of x. But the one that we don't know how to do, which we will know how to do, one of the things that we can do for using integration by parts is this integral. So the integral of the natural log of x, seems like we ought to have done it already, but we haven't. So even though this doesn't look like a product of two terms, I just said integration by parts usually involves products. You can still do it on things. So the integral of the natural log of x, the integral of the arc sine, the integral of the arc cosine, all those things that we haven't done yet, we can address using integration by parts. And the kinds of integrals we're talking about besides the integral of the natural log of x is x times the natural log of x, or x squared times e to the x, or e to the x times the sine of x. So they typically involve a polynomial term, a logarithmic term, an exponential term, a trig term. So you can see we have polynomials, natural log, e to the x, sine of x, and they're all products except for this one. But again, we can still use integration by parts to do that. We know how to take the derivative of those functions. We just use the product rule. If we had x times the natural log of x, we'd take the derivative of the first times the second plus first times the derivative of the second, whatever the opposite was. Okay, so this is the derivation of the whole thing. So if you just want to pay attention, I'm not going to test you on the derivation, but so you can see we start with the product rule, or at least we remind you of the product rule. So the product rule says if you have two functions, f of x times g of x, like over here, you know, if we took the derivative of the product, you take the first function multiplied by the derivative of the second plus the second function times the derivative of the first. And what we're going to do here is to simplify just the derivation, we're going to let u be one of the functions and we're going to let v be another one of the functions. So the way of rewriting the same thing, the product rule, but using u and v, so use the first function, v is the second function. So it's u times dv dx plus the second function times the derivative of the first. Okay. We can also, you know, there's different ways of representing the derivative. So we're also going to just for the moment change the notation. Instead of using this ddx notation, we're going to use the prime notation. So that kind of looks like, remember that's what we did with the integration by parts. We tried to take something like we started here and moved to there, so then we could integrate this, which was just u times v. So it's very similar to the integration by parts if you think about it. What we're going to do in this case, instead of collapsing two terms into something like this, we're going to take I forget which one it is, I think it's this one, and break it up into two parts. But it's not going to be, we're not breaking it up like this into those two parts. We're going to take this one and break it up into that part and that part. And the whole idea is that I can't integrate, say, this part, but I can integrate this part and I can integrate that part. So we're just manipulating the original function from something we don't know how to integrate into something we do know how to integrate. Okay, so I guess you could, yeah. So in this case, we just multiply this product rule in this notation by dx. So everything gets multiplied by dx. And then we integrate. So we're going to integrate u times v prime dx is equal to the integral of u v prime dx plus the integral of v times u prime dx. Okay. But the integral of u prime, yeah, just like with the integration by parts, the integral of u v prime quantity prime dx is just u times v. So this is going to end up just being u times v. This is going to be the original integral, and this is going to be the other part of the integration by parts. So we're going to solve for this in terms of that and that, ultimately. And this is just some notation stuff. Let's just move along here. Okay, so as I said, this integral just becomes u times v, just like with integration by parts. And we solve for this term. So that's the first term of part of the product rule. We start off with this product rule, and this was, we broke it up into two parts. We're going to solve for this. So it's going to end up being the integral of u dv, this term, is equal to uv minus the integral of v du. So that is it. That's integration by parts. That's the equation. We'll write that down a lot. And what we need to do is take the original integral that we don't know how to solve, identify part of the integral as u, part of the integral as dv, and then um, we know what u is, so we can just plug that in the right-hand side. dv, we can take the dv part and integrate that separately to figure out what v is. So this part's usually pretty straightforward. And then this integral, we couldn't solve this integral, but we can now solve that integral. So let me just demonstrate it on an example. The basic procedure. So let's say we have the integral of x times e to the x dx. So the first step is identify u and dv. So we're going to take part of this expression and we're going to call it u. And there's certain rules, but I'm just going to tell you what I'm going to choose right now. Okay, I'm going to choose u to be x. Therefore, dv has to be the rest of it, which is e to the x dx. So you have to, the dv part always includes the dx. So the question is, do I put the x with the dx, or do I put e to the x with the dx? Okay, so that's the first thing you do. Now, in this, so now I have u. I don't have v yet, and I don't have du yet. The only thing I have is u. So how do I get du? Well, I just take the derivative of u, whatever I've chosen to be u in this expression. So it's just like, it's kind of like u substitution type calculation. So du in this case is just the derivative of x is 1, and you multiply it by dx. So it's exactly the same procedure we use for u substitution. So du is just dx in this case. Now v is, what you do is you integrate dv. So to find the v in this integration by parts expression, which I need both here and here, I take what I've chosen to be dv and I integrate it. And so one of the rules is you choose dv as being the most complicated integral that you know how to do. So I do know how to integrate e to the x, so that seems like a good choice. So I said that the v part of integration by parts is just the integral of dv. Well, I chose dv to be e to the x dx, and that integral is in the table, is in your tables, so I can do that. The integral of e to the x is just e to the x. Now I don't add c, just like with the integrating factor. I don't add the constant c. I just integrate it by itself. Okay, so what do I have? I have u, which is what I need there. I have now I have v, which is the green. Oops, wrong color. So v is green. So I have v, and I have du, which is, what color is du? It's black. Okay, so I have du. So now that I have identified u and dv and then calculated du and v, I can say that the integral of x times e to the x dx is equal to u, which I have identified as x, times v, which I've calculated to be e to the x, minus the integral of v, which is e to the x, times du, which is just dx. Okay, so let me again underline everything I've done here. Here's x, here's u, v was green, so here's v, and here is du, which is red. Well, I already, no, du is black. Okay, so that's where I get all those things from. So all I have to do now is, I've already got the first part. All I have to do is just do this integral, and now I can do this integral. You know, this original integral I couldn't do, but now the new version I can do. Well, the integral of e to the x dx is just e to the x. So what I can say is the integral of x e to the x dx is equal to x times e to the x minus e to the x. And there you go. That's the answer. So that's the basic idea. Of course, it's not that simple. The hardest part, there's a couple of hard parts. One is just choosing what what part to be u and what part to be dv initially. Now, if you don't believe me that that thing actually is the right answer, you can always take the derivative of it and see if it comes back to the original expression. So what should happen is if I take the derivative with respect to x of the right-hand side, I should get the argument there, and I forgot my arbitrary constant c, so make sure I add that. So if I take the derivative of the answer, what happens is you've got the first term is a product, x times e to the x. So we use the product rule. So you're going to take, the product rule says you take the first term. So this term here, when you take the derivative, you're going to get x times the derivative with respect to x of e to the x plus e to the x times the derivative with respect to x of x. So that's this part, okay? And then the second part here, the derivative of negative e to the x is just negative e to the x. So for this product, I get two terms. This, I just get one term. The derivative of e to the x is just e to the x. The second term, the derivative of x is 1. And you can see that this term cancels out with that term, and you're just left with x e to the x. And I had the arbitrary constant, but that drops out. So you can see that it worked. Okay. So if I take my answer that I got using integration by parts up there, take the derivative with respect to x, I should get back to my original argument, which I do. So it did work. It does work if you do it right. Okay. Doesn't mean you have to check your answer every time, but that's the concept. Okay, so here's the next. Let's do one more, and then we'll talk more about how I make these choices. I'm going to move this over here so I can go through the thing. So this is x times the natural log of x. So it's another product of two terms. I know how to take the derivative of x, that's 1. I know how to take the derivative of the natural log of x, that's 1 over x, but I don't know how to take the derivative, pardon me, the integral. I don't even know how to do the integral of the natural log of x, so there's more than one problem there. So in this case, you might say, well, on the last problem you chose x to be u. So again, let's remember where we're starting from before we even go anywhere. What we're trying to do is we're trying to use this expression. The integral of u dv is equal to u times v minus the integral of v du. So to be able to use this, I have to identify something as being u and something as being dv. Last time we chose x to be u and the other part to be this part to be dv. In this case, that's not a good choice, okay? So I'm going to choose u to be the natural log of x, and I'm going to choose dv to be the other stuff, which is x times dx. So I need, in my right-hand side, I need du, so I need to take the derivative of this thing, which is 1 over x dx. And here I need to integrate it, so the integral of dv is the integral of x dx. And the integral of x dx is x squared over 2. So v is x squared over 2. So again, I have u, which I need. I have du, which I need here. And I have v, which I need there and there. So I have everything I need to plug that into my expression for integration by parts. Okay, so then I'm going to do it. That's what I'm going to do next. So I'm just going to make those substitutions. So what this says is that the integral, my original integral, x times the natural log of x dx equals u, which is the natural log of x, times v, which is x squared over 2, minus the integral of v, which is x squared over 2, times du, which is 1 over x dx. So again, this is u, this is v, and this part's du. Okay. So we're done with the first part. We're just going to move the linear stuff to the beginning. And here we're going to simplify inside. We'll factor out the half. So we got a half there. And we got x squared divided by x. So what that leaves inside is just x dx. And then we do the integral. So the integral of x dx is x squared over 2, and we add arbitrary constant. So the final answer is x squared over 2 natural log of x minus x squared over 4 plus c. So the integral of x times the natural log of x dx equals that, ultimately. Now the reason I didn't choose the natural log, because if I had chosen the natural log of x dx to be dv, I don't know how to take the integral of the natural log of x dx. It's not in my table. The derivative is, but the integral isn't. So that's why in this case I had to choose x dx as dv instead of the other way around. So there's certain decision making things you have to do. Okay, so now let's look at the rules here. So we'll come back. Well, we did that one already. Okay, so here it is, procedure. So you start with some integral, which is the integral of u dv. You have to somehow identify which part of that integral is u and which part is dv, because the part that you choose as u, you take the derivative of, and the part that's of dv, you take the integral of. So the rule is dv is usually the most complicated part that fits a basic integration rule that you can find on page 520 in your book. It's the same, or the thing in your front of your book, the list of all the integration rules. So for our two examples, dv, the first one, dv, was x, or e to the x. So e to the x was more complicated than x. And because it was more complicated, but I knew how to integrate e to the x, then I chose that as being the dv part. Whereas in the second problem, I couldn't choose the natural log of x dx to be dv because I don't have a basic integration rule that tells me what the integral of the natural log is. So that's why I had to switch them around. But I did know how to integrate x dx. And u is usually a function whose derivative is simpler than u. So typically polynomials, any polynomial is the derivative of a polynomial is simpler. For example, x squared, you take the derivative of that, you get 2x. So a linear polynomial is simpler than a second order polynomial. So 90% of the time, if you have x squared or x cubed, something like that, you do choose that for u. There are a few special cases like the natural log of x where you don't do that. But so that's the rules for choosing u and dv. Okay, so once you choose u and dv, you calculate du by taking the derivative of that, just like we do for u substitution. You calculate v by integrating it using the integration rules on page 520, Once you have identified u, calculated du and v, then you take your original integral and break it up into two parts, hence the name. And you just plug in what you've figured out in the previous steps, and hopefully you can integrate this. And you integrate, you got the answer. So it's I think that's the last step. Yeah, okay. So I'm going to do another example. So let's say you have the integral of x times the sine of x dx. Again, I know it's not an integral that's in the book. So I can't use just the book. I can't use substitution because the argument of the sine function is just x. So it wouldn't really, all it would do is just rewrite the function in terms of just a different variable, but it wouldn't really help me out any. So we can't use substitution. So why don't you write down what you think u should be and what what u should be and what dv should be based on what we just talked about. Should be pretty obvious in this case. Remember, the dv part has to have the dx along with it. And it's really just like the first problem, except we have the sine of x instead of e to the x. Okay. Okay, so there you go. So, u, we said the derivative of u usually is simpler than the original function, which it is. And dv is the most complicated integral of the two that I can use my tables for. And I do know what the integral of the sine of x is negative the cosine of x. So go ahead and calculate dx just like in u substitution. Calculate du, and then integrate dv. So integrate the sine of x dx. Remember, you don't have to put the arbitrary constant. Yeah, Daniel.
So since it can work either way in this situation, if you were to use sine of x to be u, you could take the derivative of the cosine. How does that?
Well, if you think about it, the derivative of the sine is the cosine. So really that's not simpler. So you wouldn't want to choose, you really can't choose the sine of x to be u, even though, because it doesn't get simpler. It just stays the same complexity. So if you had e to the x, the derivative of e to the x is e to the x, so it's basically exactly the same. In terms of trig functions, the derivatives are about the same complexity. So that's why you have to choose u to not be the sine of x. Okay, does that make sense? What would happen is if you did that, you'd probably be back to where you started. I don't think you don't get anywhere. That's doesn't improve things. Okay, so there you go. So the derivative of x is 1. Multiply 1 by dx to get du. And the integral of the sine of x dx is negative the cosine of x. So that's the first step. Then you plug into, so we chose u and dv. We calculated du and v. Now we plug into this. So go ahead and plug the numbers in. And I'll give you a few moments head start. If you feel pretty confident you've got the right choice. Well, actually, there's no choice here. You just got to plug them in there. Just go ahead and finish the integral, the second integral. or the integral that's on the right hand side. And okay, so that's the after you've plugged it in there and simplified. So u is x, dv is negative cosine of x. I mean, u is x, v is negative the cosine of x. I just moved the negative sign out in front. And then here you have negative, because that's negative over here. And then you plug in v, which is negative cosine of x, times du, which is just dx in this case. So the negatives cancel out. So that's where we are. And then the final thing is you integrate, which means you integrate the second term. And that is, again, that second integral now is one that's in the book. So the integral of the cosine of x is just the sine of x. So that's your answer. Anybody got any questions about anything so far? Yes.
So you include the arbitrary constant at the end, but not...
Right. Yeah. Because you don't... I mean, ultimately we need an arbitrary constant in there, but you stick it in too early and you'd end up with an extra term that you don't need. So yeah, it's kind of like integration by part. I mean, integrating factor. When we calculated the integrating factor, we didn't put c in there. We always put it in the last integration that we do. Okay, now let's look at another one. So let's say I have the integral of x squared cosine of x dx. So instead of having x, I have x squared. Oh, you're doing it too, huh? Yeah. So again, the rules you use are that u is a function whose derivative is simpler than the original function, which still applies here. The derivative of x squared is 2x, so that is simpler. You go from a quadratic to a linear. The second part, dv, is an integral whose something that you can integrate using the table. It's the most difficult, and integrating a trig function is more difficult than integrating a polynomial. I mean, integrating, as you know from experience, you guys are good at integrating polynomials. That's the easiest thing. So using that philosophy, the only thing that changes is x squared. U becomes x squared. dv is still the trig function part. And then you take the derivative. Instead of the derivative being 1, the derivative here is 2x, and then you add your dx on the end. And then v, the integral of the cosine of x, is the sine of x. I just changed that so you have something different. Okay, so we've got everything we need now. So plug them in there. So you got the integral of x squared cosine of x dx equals u times v. minus the integral of u times dv. What's my problem here, though? Right, yeah. So typically when you've got something other than just x, if you got x raised to a power, whatever power it's raised to, you have to do integration by parts multiple times. Because what we have now is basically what we had over here. We've already actually figured it out, right? So we can actually use the result. But what you would do is when you are, let me just factor out the 2 here. So what we're really doing is, so we got the first term, that's completely done. If I factor out the 2, I have the integral of x times the sine of x dx. And so to do this, you would do it separately. So I would take a little break here from this problem. I'd come over and write that down, and then I'd have to go through the whole thing, and then I could say, oh, there's the answer. By using integration by parts again, I can solve this integral. So ultimately, the final answer here is going to be equal to x squared times the sine of x minus 2 times the result of this integral, which I just did, which is negative x cosine of x plus sine of x. And I just add an arbitrary constant at the end. I don't multiply it by 2 or anything like that. And then finally you would go ahead and multiply the negative 2 out amongst the 2 terms. So the final answer is going to be x squared sine x plus 2x cosine x minus 2 sine x plus c. So that's the integral of x squared cosine x dx. I usually put at least one on the test, which is not this test that's coming up, not chapter 8 test. One where you have to do integration by parts twice. It's usually, x squared e to the x squared sine x squared cosine x. And you have to, when you get to this point, you'll say, oh, I got to go over here and just do the whole thing over again, get the answer, then take that result and plug it back in for that, and then just clean things up a little bit. And you usually end up with something where you got x squared times a trig function plus x times a trig function plus, it's an earthquake here, a constant times a trig function. They alternate like that, sine x, cosine x, sine x. Okay. Now here's the one that's going to be a little different. So if you did the problem x squared sine x, it's going to be pretty much the same thing. You're going to have, instead of sine, you're going to have cosine. If I did e to the x, basically the same thing. Let's look at the natural log of x dx, which we haven't. We've done x times the natural log of x dx, but we haven't done just the natural log of x dx. So we got to choose part to be u and part to be dv. Well, it's pretty. Initially you might think I can't do it because I really don't have a product, but I do really have my product. If you think about it, a lot of times you have a product, you don't really realize it because this is equal to 1 times the natural log of x dx. Okay, so I'm multiplying 1, which seems like I don't have to worry about it, but remember, if you integrate 1, you get x, so it's not completely. So, so what part is what are we going to call? We're going to call it one part u and one part dv. And we kind of, if you go back to the one of the earlier problems we did, where we had the natural log here, we had, I think, go back one more here. We let u equal the natural log of x and dv to be x times dx. So it's the same thing. We can't use the natural log over here because we don't know what it is. That's what we're trying to figure out. Okay, so in this case, u is just is the natural log of x, and dv is just dx, or 1 dx if you want to call it that. So go ahead and take the derivative, and the integral of dx is just x. Actually, the integral of 1 dx is x. So I have to tell you my instrument story, and I got my new trumpet, which it sounds a little better, but it doesn't sound a huge amount better, And I was kind of expecting that, but because you think about an instrument, especially a trumpet. I mean, what can mess up the sound if you have the same shape? Somebody makes a trumpet with the same shape, and you have the same mouthpiece that you've used forever, which is a good mouthpiece. It's not a cheapo mouthpiece. And so there's just some slight differences. The valves are nice. That's if you have a cheap trumpet, the valves don't slide as well. Also, the tuning slides, the slides that you use to tune, those are so much nicer. But the sound, so I'm trying to decide whether I should be disappointed or not, or should have I expected that. I don't know. So the funny thing was, I bought it on eBay, and I always have these lingering worries that I'm being scammed or something like that. I'm a skeptic. Steve the Skeptic. That's what my wife calls me. Steve the Skeptic. Actually, she didn't call me Steve. That was what they call me at Westvaco. Steve the Skeptic. So I'm a natural skeptic about things, and so I've been thinking, is there any way this could be a fake? Did they give me a counterfeit trumpet? Okay. So I was on the internet looking at pictures of the instrument, because they have the brand name. It's inscribed in various places. I'm looking at the picture and I'm thinking, okay, it looks rigid. Looks pretty authentic. And then I opened up the trumpet case, and there's a use and care manual in the trumpet case. So I open it up, and it's like an authentication thing. It's in Chinese because this is a Taiwanese trumpet. And I open it up, and I'm looking, and the instrument that's in the booklet is not the same as my instrument. So I'm like, why is that? Why do I have a different booklet? It's the same company, but it's instead of a 7,772, it's a 5,000. Okay, the trumpets have different names. It's also a C trumpet instead of a B flat trumpet. Well, that's weird. So I emailed the guy and I said, "Hey, why do I have the little booklet that says this trumpet and this is my trumpet?" And I think I know what it is, but the fact that he hasn't emailed me back's bothered me. I think what it was is the case is for the other trumpet, and he just put my trumpet into a different case because he didn't have the original case for the nicer, because this is a nicer trumpet. So he probably put it into the case, and in the case was the original care and use manual for the other trumpet. And I think that's a reasonable explanation. So I don't know why he's not answered my email. So that bothered me a little bit. But now the guy who's the good trumpet player in our band, he has the same brand instrument. So tomorrow night I'm going to try his instrument out, and just to see if I notice any difference or not. I mean, I'll accept it if that's just the way it is, that you can't really make a trumpet sound that much better by buying an expensive trumpet. You can make it look nice and all that kind of stuff. So that's my latest. I'll feel good when I've convinced myself that I spent the money on a real trumpet, not a fake trumpet. But Yeah, so far it's kind of interesting because they have, these are custom built trumpets. It's like you buy a car with a certain kind of seat and a certain kind of color. This one you can choose the material it's made out of, whether it's a large bore or regular bore, whether it's a lightweight or regular weight, or you can choose whether it's the tuning slide is whether it slides over the tube or inside the tube and all this kind of stuff. So it's and it has that engraved on the bell, which does agree with what I have. I mean, everything it should be okay, but I'm still not. I'm 95% certain that I have a authentic good trumpet, but I'm not. I want to eliminate the 5% chance that I got taken. So anyway, okay. So this is so if you take the derivative of the natural log of x, you get 1 over x dx, and the integral of v is just v, and the integral of dx is x. So you plug that into your integration by parts formula, and so you get u times v minus the integral of v times du. Okay, so you simplify, well, we'll move the x to the front, and x times 1 over x is 1, so you just get 1 dx. So we simplified the integral, the term in the integral, and the integral of 1 is just x, so you get x plus c. So the integral of the natural log of x dx is x times the natural log of x minus x plus c. So there you go. So, what is today? Today is Tuesday, and the test is Tuesday. So I'll wait till Thursday to assign homework from this section. I think that's enough for today. So.